Good morning, everybody, and welcome to the JKMRC Friday Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australian and global society. Today is my great pleasure to welcome Marko Hilden. Dr. Marko Hilden is a mineral processing engineer with 17 years of experience, with over 17 years of experience bridging research and industry. As a senior research fellow at the JKMRC, he leads innovations in combination, modeling, and simulation, helping to improve prediction of milling performance at production scale. His work includes advancing SAG mill models for multi-component feeds and dynamic simulators, as well as developing tools that link combination to mineral liberation. Marko's expertise expands HPGR, stirred milling, screening, and circuit design for complex flow sheets. Before joining JKMRC, he worked in iron ore and coal operations, gaining hands-on experience in large-scale processing. His PhD research in in industrial screening earned him the Ian Morley Prize in 2007. Today, Marko collaborates with industry partners and mentors postgraduate students driving practical solutions for mineral processing challenges. Today, his talk will be about connecting the mine with the mill using JKMRC stockpile model. Please help me to welcome Marko.
Thanks very much for that, Dawson. Thanks for coming in person and online as well. Today I'm going to talk about the, sorry, can you just check the microphones? Yep. Talk about the work that we've been doing on the JKMRC stockpile model. So some of this work is fairly old, but we've done some more work recently as well. Dawson's just acknowledged the traditional owners, so the Turrbal and Jagera people. Let me now talk about, just describe the kinds of material handling processes that we have in the mining industry. So one of the main types of stockpiles we have is the ROM or coarse ore stockpile. We're fairly familiar with these stockpiles, so they decouple the mine and the plant to manage variations in ore feed. They typically have like a 12, 24-hour life capacity, and they blend properties of the ore, so that gives you a more consistent feed grade and size, and that helps the plant run more stably and give a more consistent milling and flotation performance. So they definitely add a lot of value to the process, but the stockpiles are large and they're a significant infrastructure cost as well. So here's a basic schematic of a coarse ore stockpile. They get fed from above usually, and then they have a series of feeders below to extract material from the base of the pile. One thing to note is that not all of the volume in the stockpile is live. So often only around 30% of the stockpile volume is considered live, and then you have this large dead volume around the stockpile that can't be gotten at. So when you're managing the stockpile, you need to be aware that not all of that volume in the pile is accessible. And then the material from the apron feeder goes off to your often a SAG mill or some other process. There's lots of different designs of coarse ore stockpiles. So this is a iconic design that they've used at the North Parks mine. So it allows ore to come from two different sources, for example, an underground and an open pit, and transfer material from one side to the other for getting a good blend to both SAG lines. Another way of managing stockpiles and to expand their capacity is to use a tripper or shuttle conveyor that goes backwards and forwards, making an elongated stockpile, and then you can have multiple conveyors coming out from underneath, under the pile. So this is a covered elongated pile at the Aitik mine in Sweden. And you can also have these slewing stackers, like at Telfer has a couple of these slewing conveyors. So that's a motion where a boom goes in a sort of a circular motion. And there's also a luffing motion, which causes the boom to go up and down. So you can have various different kinds of designs, allowing the stockpile allowing the feed to be spread over a larger area. There's many other kinds of stockpiles as well that you can encounter in a mine. So, for example, in the iron ore industry, they use grade control or pre-crusher stockpiles between the mine and the crushing plant. So they allow you to blend ores of different grades and properties by first dumping them from a truck and making a big pile of dirt, which you then again reclaim using front-end loaders before, and then send to the crusher. Iron ore and coal as well, they produce a lot of, they have product stockpiles because they're bulk commodities. In iron ore, typically they have a run where the stacker runs backwards and forwards for up to a week, creating a large stockpile before it gets loaded out to either train or ship. And while they're building that stockpile, they can tweak the grade to make sure that the final stockpile is on spec. Potentially, we can also consider the blasted muck pile as a stockpile. It's basically just a pile of loose rock. When if we're modeling a stockpile, potentially it can also be used for this sort of application as well. And around the plant, we can often see silos, bins, or hoppers, and these are just piles of rock within walls, and we can also model those as using the same methods, ore flow confined in a bin. So we began this stockpile modeling program about 5 or 6 years ago with a PhD student. And we identified that there's various different kinds of, or various different ways of modeling stockpiles. So there's simple queuing models. So basically, you just have a first in, first out, or first in, last out kind of approach, and there's a few other permutations of that. For our purposes, it's too simple, and it doesn't really explain how the blending works in that stockpile arrangement under different conditions. There's a lot of work that's been done on stockpile mapping that gives you a sort of a 2D surface representation of the stockpile. And you can also include potentially hyperspectral to add grade information to that. But what we need is a 3D representation of what's in the pile. There's also been a number of publications on using DEM modeling to model granular piles. They suffer from the problem that these piles contain huge numbers of piles, billions and trillions of particles, even if you have a fairly coarse, lower size cut point. So when you see these models, they're generally, they use a technique called coarse graining to improve the speed. And there's some really excellent work done by a guy called Martin Serban, whose DM picture shown there. And he's combined cellular automata, which I'll talk about soon, with discrete element modeling to improve the performance of that. But cellular automata started off quite a while ago with some famous names like John von Neumann and John Conway and so on. And they've shown that you can have, you can define cell behavior. So you can, instead of modeling particles, you model discrete cells that only interact with their nearest neighbors. And you have some simple rules that describe how that cell behaves when one of its neighbors has a certain property. And the most basic CAs store just an integer state for each cell, and they don't pretend to have to incorporate the full physics of the system, but even with the simple rules, structure and fairly realistic behavior can emerge from just these local rules when you apply those rules across the whole system. So these sort of models have found some practical use in modeling granular systems, especially for underground mining methods. The real advantage of these is that they're fast compared to DEM. So there's been quite a bit of CA modeling, even at the JKMRC. So Raul Castro, for example, did a significant amount of work on CA modeling, and he's continued to do that, to apply CA to date for block cave modeling. There's various commercial codes that also offer this behavior, as I've learned more recently. Galti Asbjörnsson from Sweden has also developed a CA model, although he wasn't calling it that. It works on similar principles to model bin dynamics in a dynamic simulation. And there's the Martin Serban's work as well that combines CA and DEM. He's put together a digital twin model that looks quite impressive. So our technique, we're calling it a continuous cellular automata model. So rather than having a discrete, a singular state in each cell, we're setting up a 3D grid that, and with each cell storing multiple properties. So the properties include a state, so describing the type of cell. Each type of cell can have its own behavior. So for example, we can set up base cells, colored there in red, that only that are fixed in place and they don't move or interact with other cells. We have full cells that are filled with ore. There's surface cells on the surface level, and there's empty cells above that. So there's also a parameter for filling. So the surface cells are allowed to have a filling between 0 and 1, and that allows you to have any angle of repose. Whereas if we only allowed full cells, we could have a slope of 45 degrees only. The cells can also include a characteristic size, grade, or any other additive property, and also the time that you added that material to the pile. So in our model, the it's a time stepping model, and in each time step, there's an increment of feed, discharge, there's a void propagation, and a surface flow calculation that gets performed each time step, which I'll go through one at a time. So in the stockpile feed, we need to decide where the new increment of material is added to the pile. So, for example, if you're using a conveyor, the conveyor has a trajectory that you can calculate which cell the material lands on using the conveyor height, angle, and speed. And we can also describe segregation of the feed into a coarse fraction and a fine fraction, which we can place separately into different columns. And that increment of ore, which is less than a full cell, is added to the pile. We can combine it with the material in the existing material in that cell, so therefore requiring additive properties. And then the height what will happen then is there'll be a height difference between adjacent cells that can exceed the angle of repose. So we need to do something about that. The next steps are discharge and propagation. So an increment of ore can be removed from the base of the pile at the location of the draw point. So you can have multiple draw points and you can extract material from multiple points if you wish. Then if the draw cell becomes empty, a propagation rule is triggered, and that means basically one of the cells above the void cell drops into the void based on a probability rule. So it's a simple probability rule that we've followed Raul Castro's approach, and that is basically the inverse of the distance of the center points of the cells. And once that void propagates, there's a new void in the layer above, and that process is repeated to give a random path up to the surface. Again, when a cell drops down, that can create a height difference more than the angle of repose. So you've got an unstable surface. So if that random path is repeated multiple times through the course of the simulation, you end up with a movement of material from above down to the draw point following this sort of parabolic shaped flow pattern that evolves. The final step in the model is a surface flow. So basically it's just searching the surface for columns that are exceeding the angle of repose, and then moving the amount of material required to restore the angle of repose. And so the properties of the lower cell is combined with material from the higher column, and this is done each time step. In stockpiles, we often have segregation. So, if you have a pile of, if you approach a pile, you'll often see coarse material that rills down to the base of the pile. On that picture on the left, I think that's Jeremy for scale. And you can see this segregation as well in DEM simulations, and also in this little toy machine, sort of what do you call it, hourglass kind of thing. So the way we've approached modeling segregation is again with a simple rule. there's a model by those guys, and it says if you have a mixture of particles, then it can segregate into a coarse and a fine component. So what this rule has is a minimum and a maximum value as well. So below, in this case, 40 millimeters, it's all fine material, and it's saying fine material won't segregate. So if all of your material is very fine, it's not going to segregate. Likewise, if it's all very coarse, if it's all just coarse particles, that's not going to segregate either. But if you have a mixture of the two, it will split into a coarser and a finer fraction. So in our surface flow algorithm, we have the material first being split into a coarse fraction and a fine fraction. And the coarse material flows down to the lower cell, and the fine fraction stays in the higher column. And if that process is repeated over all of the columns, you end up with a segregation. So that model needs to be calibrated, of course. So Zimming developed this segregation model. So basically, it's a cookie cutter that you put on top of your stockpile, and you can then size those concentric samples, and you can see that there's quite a wide range of particle sizes that you get from analyzing it like that. And then you can do a simulation of the stockpile and tweak that those segregation parameters to match those properties. And you can see as well in a slightly larger pile that he created, that the center of the pile, so he's basically sliced the stockpile horizontally, and you can see there's the difference between the inner and the outer is quite dramatic there. So this is again from Zimming's work. So he went to the Las Bambas site with Mosen, and at that site they have a very large coarse ore stockpile with about 105 kilotons live capacity. There's a conveyor feeding the stockpile at about 8,000 tons per hour, and 2 SAG feed conveyors. And there's 8 apron feeders taking the material into the SAG mills. We used pi data to input as inputs to the model. So feed tons per hour, particle size. So they had a particle size analyzer on the feed conveyor to the stockpile. And we used the discharge tons from each conveyor and the feeder speeds to work out where the material is being drawn from. The stockpile heights and the discharge product sizes were used for validation purposes. So this stockpile has height sensors, but it's not right at the top of the stockpile. It's actually offset to the side. And you can see that as the material is fed to the stockpile, it doesn't always land on the same side of the stockpile. So therefore, it's important to actually model that trajectory correctly and find the right impact point. You can also observe here the feed segregation in the feed. The fines tend to separate out to the underside of the stream, and coarse material to the outer. So that's what's causing one side of the stockpile usually to be coarser than the other side. So a 3D model, this is showing the animation of the stockpile model in action. So it's made up of about 80,000 cells, and each cell represents a 3 by 3 by 3 block of ore. So it's fairly coarse size, but it's a very large pile as well. You can see that it forms this octagonal pyramid shape, and that's a function of the way the CA model is set up. And you can also see that there's some segregation. So there's coarser material on the side away from the stockpile. So that pillar at the back is the thing that supports the feed conveyor. What you can do with that is you can estimate the predicted stockpile height, and the stockpile from the height from the model tracks the measured height quite well. This is about a 2-month window, I believe, in this graph. And likewise, you can compare the simulated and measured product sizes going to the two lines. And if you look closely, you can see that the line 1 is actually a bit coarser than the other line 2, and that's because of the trajectory segregation. And you can see it. Some analysis was done as well on the performance of the two SAG mills in response to this difference in feed size. So it results in a difference in throughput and other performance characteristics. So the other site we've implemented this at is the Batu Hijau site in Indonesia. It's a elongated stockpile fed from a tripper conveyor. And again, similar sort of data, but this one had 5 level sensors distributed along the length of the stockpile that were used for calibration. So here's the 3D model running. You can see that the material is being added as the tripper goes backwards and forwards, and feed is actually fed at 2 points on either side of the columns supporting the tripper. And after a while, the stockpile goes into a shutdown, or the plant goes into a shutdown. The levels drop off right now, and then it starts up again after the shutdown. So this is a roughly 1-month window here, I think, simulated here. Again, we can look at the stockpile height because of the motion of the tripper. The levels are constantly going up and down, and so you can have you can compare the model and the sensor. In some cases, you can see that the sensor actually, just where it's marked there, the sensor actually jumps up quite rapidly, whereas the model predicts that it's actually started rising already. So by having both measurements can be a useful thing as a backup to a sensor. The other thing that you can do with the model is calculate other information, like, for example, the stockpile total and live capacity, and the live capacity even above each feeder. So you can see here that the far, on the right, you can see that the far capacities, the blue and the purple, are actually very low. So they're actually not able to get much ore from those feeders, whereas most of the action is actually in the center feeders. So you could actually use the model to do what-if experiments on what if you change the placement of those draw points, and how would that affect live capacity, for example. You can also look at the D80 above each feeder And that would be a useful piece of information when running a SAG mill, for example. So you can see that the front and the back feeders or the center feeders don't always have the same size, and that could allow you to adjust where you're drawing from. In our modeling, we got to the point of having a simple user interface that you could run a batch of pi data through it, update the state, then run another batch of pi data through the system. This is mentioned in the SAG conference from a couple of years ago. The intent was to turn this into a soft sensor, and we were most of the way there. So a soft sensor is can act as a backup of and provide additional information for a process. And Tanya's talked a lot about the other soft sensors that we've been developing in our group. So for this stockpile, we could estimate the profile, D80, age distribution of material in the pile, total tons and volume, live tons and grade and size above each feeder. And this type of modeling would it's a model driven approach, a white box approach, which uses the available process knowledge and first principles, and it's easy to understand compared to a machine learning based model. The other application is that we want to use this for is for controlling SAG feed size. So there's potential to use the information from the draw points to track the feed size to the SAG mills, and also ensure that you're not depleting all of the fine material from the stockpile before the next crew arrives. More recently, we've been working on applying the stockpile model to material tracking and geomet. We're not in a position to talk too much about it, but I'll explain the direction we're heading in. So geomet, it's an interdisciplinary approach, combining a bunch of different disciplines, and many of which we have here. And adding material tracking to geomet is complementary, because the material tracking provides the real-time visibility of the ore movement and quality, and geomet gives you the predictive models of how that ore behaves. But putting these together allows us to have a dynamic mine-to-mill optimization, and to have this feedback where we can, from the block model, track material to the stockpile, know when that tracked ore arrives at the plant, and compare the attained mill throughput with a prediction, and then feed that back. So it's an important capability that that this stockpile model has potential for. So another important application is for reconciliation. So in reconciliation, we want to monitor the ore flows across the value chain and ensure that what we mine, move, and process can be reconciled with models for reporting. So we need to do this, but traditional reconciliation is usually done on a sort of a snapshot basis. You're using assays that have a time delay. There's usually at least a manual aspect to the data entry and analysis, and it has a fairly low frequency. With the direction that everyone's going in is real-time tracking, where you have this rich ore body characterization information from the pit itself, using online sensors, GPS on all of the mobile equipment, and if we can also predict what's happening in the stockpile and model that, we can complete that, that loop to pass that information to the process plant, and also apply advanced analytics to the process. So we've been working on modifying the model to track IDs of material through the stockpile. So what we can now do is track ore parcels through the stockpile rather than concentrating on individual grade properties. For example, in iron ore, there's many different quality parameters. Rather than tracking those all, we're tracking a single ID that you can then link to a database. And in this application, ore can be handled using haul trucks, shovels, or front-end loaders and dozers. And those material movements tend to mix those IDs. And so we're basically developing a model based on the stockpile model to do that. So the brief is really to model the truck dumps. So given the GPS coordinates, heading, payload, and ID, develop a state model for where the material is placed. Then model the dozer push based on the GPS path, heading, and blade height. And these movements mix the ore properties, and then sometime later, front-end loaders can dig material from the stockpile, again using GPS coordinates, heading, and bucket mass, and then the model outputs the contents of the bucket. So we can estimate what material was extracted from that pile when dug from that particular location. So this model, the previous models are time-based, so basically taking samples or running every few seconds, whereas this is an event-based model. So every time there's a material movement, the state gets updated. And then the IDs that are extracted at the end of this can be then passed on to the next process in the chain. So it can be a part of a mine to port solution. There's also, we also have the ability to model silos. So here's a gratuitous video of that. And you can also stimulate bins with multiple outlets. So this is an example of a bin that I was curious about why material at the two outer parts of the bin that were going to the crushers, why they were coarser than the middle one, and this model explains quite clearly. Which is why most of the time when you have these sort of bins feeding crushers directly, you have a shuttle that goes backwards and forwards, like so. And so in conclusion, I think, am I running out of time? Not quite. So our CA model, with fairly simple rules, offers a pragmatic fit-for-purpose method for modelling material handling. And this capability, we think, is an important part of the geomet material tracking puzzle to enable real-time optimisation. There are many other applications that we could apply this model to that we haven't done so far, but fully aware of. Soft sensors, digital twins, process control, design what-if studies, and so on. I'd like to acknowledge we've got a team of people working on this stockpile model, so Gordon, Christian, and Joel. Zimming and Mosen for starting this process, and the several mine sites that we've been working with. Thank you very much.
All right, Marco's left several minutes for questions. So,
hi, Marko. Andrew here from Comms. So I have a sort of non-technical question. What is the importance of having that blending? Like you've mentioned several times that you want to get the blend in. Is it the same as in coffee that you're trying to get like a flavor profile that's like consistent across the thing so that when it goes to processing that it's easier, or what's the importance of that?
It depends on site to site. So the mining faces can often have very different ore properties, and it can help to blend those materials rather than having, for example, a high grade ore being processed separate to a low grade. You actually blend them together. So in iron ore, it's critical because the iron ore quality is specification is quite tight. So you really want to make sure that as you feed to the crusher, it already has a degree of blending of the ore, so that you don't get your product rejected.
Marko, hi. Grant Ballantyne from Azenco. Great presentation. I am interested in the Las Bambas. It's been presented before. Obviously, that was identified as a risk when Las Bambas was getting built, that there would be segregation across that, and that would cause downstream issues. I'm seeing another project making the same mistake now with and it's been identified, and we've been told that it'll be okay because there's going to be a deflector plate at the end of the stacking conveyor to mix the coarse and fine. Is that something that you have modeled in your process? And I guess could you comment on how effective that might be as a fix to Las Bambas?
We haven't modeled it, but it's probably something we can do. I mean, we've modeled the segregation. We've modeled it as the feed as a segregator. We could definitely model that with just material dropping straight down mixed and seeing what the difference is. It's something that we could test out, I guess. There's so many things we could do actually.
Yeah, Malcolm. Just on Grant's thing, what I do is run a DM simulation on the design of the plate, and then you can put a function in for that, for the blending, how successful is blending. So you don't have to assume it's perfect.
Yep.
And for Grant, done work of that in other companies, and it's, if done well, it's really good. Quite simple and really good. So I'd go for it 100%. I have a separate question.
My quick question was draw points, Marko. How frequently do you get draw point choking blockages occurring in these stockpiles? And would your model be useful in predicting draw point blockage?
So the model doesn't include that at the moment. You would have to actually add some
a risk factor, yeah. So I'm just thinking you could build that into your model.
Exactly. So you could have something in the model that says you could have it moisture related. At the moment, it doesn't have moisture in there, but you could add that, or compaction related. Yeah. So depending on the depth or I
was thinking something around size, distribution, and compaction related there. But yes, it's
at the moment, we've used very simple rules, and that ignores a whole bunch of different phenomena, as you'd appreciate. So it's at the moment we've been focused on basically bulk material handling in a very simple way, sort of the gross behavior of the material. But there is scope to finesse further. And
Thanks.
yeah.
I'll take my actual question if that's okay.
10 behind you as well.
All right. Just on the geomet side, Will Futcher presented last year, which they won the Seek Award for, the Red Chris case study of shovel sense. And really nice work. If you remember the work, he tracked it all using an Excel spreadsheet and trying to reconcile from the shovel to the grade at the end of the milling plant. And he only got it to work when he put a simple stockpile model in, because of the blending, and he put a height-based brute force black box backfit. So in terms of the work happening here, I would really target people who are trying to implement that, because they only fail if they don't put the stockpile model in. So more a comment, but it's a great opportunity, and it really completely transformed the ability to correlate.
Yeah, no, that's a good point, because what we're seeing is that even fairly simple models can be actually quite useful. So our model would probably be a step above what they're doing. And yeah, but it doesn't have to be full physics or full DEM or anything like that.
Thanks, Marko. It's a fantastic piece of work, and congratulations to you and the team. It's been going on a long time, I know, but you've made a lot of progress. I was just wondering about calibration, what you need to know as inputs to the model. So things like angle of repose and that lab test for looking at the relationship between particle size segregation as a function of the distance to the center and so on. What measurements do you have to make in order to have inputs to the model? Because things like angle of repose sounds like a sort of model parameter in a way.
Yeah, angle of repose, the model can actually incorporate a local angle of repose as well. But normally we just assume 38% or 38 degrees, for example. In terms of the segregation, we have that segregation test that we can use, and also tuning it to site data. So if you have measurements from site, you can tweak some of the parameters based on the measurements that you get by comparing the model with other information or survey data, particle size analysis, or so on. Yes, in a sense. Yeah.
So we've got a couple of questions online here. The first one's from Paul Greenhill. Can you comment on the level of cell blending, ID tracking / mixing that you see in the model? What are the critical variables?
Yeah, the blending depends on how much the material is disturbed. So in the stockpile, as you draw down, material naturally gets mixed as it draws. It also gets mixed as it flows down the pile. In our ID tracking, the material gets mixed as a dozer or digger removes material. So basically material at that point gets mixed as you dig, and material reposes again. So the model estimates how much mixing is being received by how much it's disturbed, I guess.
The second question is from an anonymous attendee. I say, thanks, Marko. Great presentation. The stockpile modelling currently under development looks promising and collaborative. How do you envision using it to support a mine-to-mill approach?
There's various ways we can work with this. What we're doing with this mining company we're working with at the moment is they have an existing mine to mill process, and we're supplying a key part of that, which is the stockpile modeling. So we're working directly with the mine site to give them the piece that they're missing, I guess. We're not experts in the whole chain in our group, but we're providing that capability that they need.
So I got a quick question mine now. If you're ever sort of running this at the same time in parallel with an active operation and looking to see how you're tracking, do you do sort of like a digital twin, I suppose, but in real time with something that's in operation? If that's something you do, it strikes me that the technology that the M4 Mining is developing with the drone, real-time drone monitoring and spectral analysis and LiDAR, et cetera, would be a really great data acquisition tool to be tracking what's happening in the plant. Have you had a look at that technology, and do you think that sort of approach would be useful?
Yeah, that's a really important point. So one of the things I didn't touch on is as you disturb material weights, as you place material into the pile and draw, there can be errors associated with the amount of material that you're adding and subtracting. And you can basically get a drift of the volume in the stockpile from actual. And using drone measurements, for example, is essential for correcting that. And that's one of the things we're implementing in the model as well, to basically modify the stockpile profile based on measurements. So adding the hyperspectral as well would be really powerful as well, because the stockpile model can estimate the properties on the surface, and you can compare it with hyperspectral. So that would be a good validation of the model as well. But the model still needs to track the grade information deep within the pile as well. So, but validating on the surface gives you more confidence that what you're seeing throughout the model is more or less accurate.
It was should go for some language there.
Marko, thank you for the great talk, firstly. Perhaps a very basic question, but I just wonder if your model captures pushing in action on the stockpiles, because you see that there is a live push in action on the stockpile as well to avoid sort of segregation at times, or at times it could be. Can you hear me?
Sorry. Oh, dozing is something that we're implementing in our model with we're doing the ID tracking for. So in that one of the material movements is a dozer. It turns out that the truck dumping and digging is fairly straightforward compared to the dozer. Again, it's the model that we're implementing is not a full physics model. It doesn't respond to forces or anything like that. It's just pushing material, making sure that material moves, that it flattens the ground behind it and compacts the ground. That's all we're doing. I'd like to talk more about that one, but that will be in the near future, hopefully. But yes.
So here's a geologist asking a question. So in a way, you're aiming for homogenization of the stockpile. But if you consider, say, an ag mill or a SAG mill, then if it's not homogenized, you actually get the chance for a different draw point and control the grain size distribution that's going into an ag mill. Would that sort of be a consideration that you would head towards in this modelling as well?
Yeah, so the stockpile doesn't necessarily have to be completely homogenized as long as you know what's in it. If you know where the coarse material is, where the fine material is, you can deal with it. Sometimes it could be to your advantage to be able to adjust those coarse and fine proportions. So, but yes, using the model for process control is something that we really need to do. It's definitely on our to-do list. Yeah, it's one of the important pieces of information that, and also for crusher control, right? So if you know the feed size available, you can use that in managing your crusher operation as well.
I'd just like to add to Nick's point and your response. It's generally accepted that blending is a good idea because it smooths out variations, makes it easier to run the plant. We have lots of evidence that sometimes blending is a very bad idea because if it's a flotation plant, the chemistry reacts badly. You have what's called an antagonistic effect. I have a wonderful data set that proves beyond any doubt that one of the great zinc mines of the world in North Queensland that some of you will be familiar with took a hit of 5% of recovery consistently when they blended two ores compared to running them separately. Yep. So the answer to that is to have separate stockpiles and to manage it better. Nobody ever does that because it's too expensive and too complicated. So I wondered again, this is more of a grade and chemistry thing than a particle size thing. But if you could carry that information through, could your model help with avoiding that kind of situation without spending too much money?
I don't know, but I'd like to try. Yeah.
We go at this absolutely ridiculous scale in the geomet project. And we produce a model. And we produce a model that perhaps when we come to blending and putting in the processing side doesn't reflect back in how we actually dig it up or model it. And I'm really intrigued by this. And I keep wondering why, as I said to Mosen, why in the recovery stage we end up at this sort of magical, 78 to 82%. And if we actually did something like you're suggesting and actually built the plant with optimum performance first, and then it made every model about that, we could actually do a much better job. Because at the moment, the geologists control the grade and how it appears, and then everything continues with that. Whereas our argument is maybe it should go backwards from the plant, sorry, Mosen, but I just took a...
I mean, to your point, Tim, I think we don't necessarily need to separate the stockpiles as well, because with this model, we can track the ID of the material. So we know what's the material property. In Batuhiju, actually, Marko was tagging each of the ore with the time that they stayed in the stockpile as well. So essentially, we knew how much time they have been in the stockpile, which in that case actually had an effect in the recovery as well. So therefore, we can start live inform the plant in terms of what material is going to the flotation at the moment, how much have been in the stockpile, and all of that can drive the chemistry and how you would run the flotation as well, yeah.
So
Out of time.
Can I please ask people to spare maybe 4 extra minutes and then.
Yeah, I was just going to answer that question. One of the things that I know we were doing at Metso years and years ago was the flotation circuit is a laboratory in itself that doesn't actually get used that much in terms of the information that's coming out. So as Tim has said, he was able to do this beautiful stats pick up these relationships. But if you can start tracking what's coming into the plant always tracks its recoveries. You can start to be doing these ongoing statistical analysis to kind of get an idea of the effect of blending ores, the effect of doing all these things, which ultimately can give you the answer, because there's so many variables that are impacting. It's very difficult to unpack them. But if you can start to track things so you know what's coming in, then you can start using the plant to give you the results, which can get to the underlying key drivers. Like there's lots of drivers, but what are the really key ones, and what do we need to change in terms of the feed? So I think there's a real opportunity there.
Yeah, absolutely. And like the stockpile model is only part of the overall model that you need to do what you're talking about. So you actually need the grinding models and the float models to be able to then
yes, you can. Those models can give you more whatever, but just regressions between feed coming in and performance. You don't need all of those grinding and float models to be running. So you could be doing it at a high level now, and then move once, because it takes a long time to develop all those other models. So I think there's a lot of value that can be achieved now.
Yep. A critical part though also is the time delay between okay, it's come out of the stockpile, but it's not quite at flotation yet. But yeah, that has to be brought into it.
Yeah, complementing in the same point, from the process control point of view, well, my dream will be that now that we have the information and then you can track domains or lithologies, alterations, then you can do the data analysis or the analytics to see the impact on flotation. And then you can modify your reagents based on that information when they reach to the flotation stage. So I think that is something that we should look for in the future.
Absolutely.
And also from grinding, I think a good benefit of this is that you could also do analytics to check which is the optimal size distribution to the SAG mill to optimize throughput, but also if your circuit is constrained by secondary grinding, then you can process less throughput or less tonnage, but you could put the coarser material to take that opportunity to grind that material.
Yeah, indeed. Yeah, there's so many pieces to this puzzle around real-time tracking, and really we're just involved in a part of this modeling part here with the stockpile, this advanced analytics and all this other stuff. A lot of this we already have. We've already had GPS on equipment for quite a while. Just putting this together in a better way is what we need to be doing. But it's actually a big puzzle.
All right, please join me again to thank Marko. And thank you everyone for coming. This is the last for this year, and so we'll see you again next year.